Look there, are those the pyramids of Egypt? Not quite. If you look closely, the side of this pyramid is a triangle with numbers? Yes. I have a feeling we're not in Egypt anymore. We never were. This wonder of math is known as Pascal's triangle, named after French mathematician Blaise Pascal in 1653. It's much more than just a triangle of numbers. Its two sides are aligned with ones, and each number is the sum of the numbers directly above it. So Pascal's triangle goes on forever. And like Egypt's pyramids, it has so many secrets hidden in it, such as an easy way to solve binomials raised to large powers. Remember this annoying problem on your homework? But Mom, I don't want to disturb you. Keep your head up. We'll use the power of this triangle to solve this binomial expansion. The triangle is made up of rows, and let's say the top of the pyramid is row 0, so this is row 1, row 2, and so on. We want to raise x plus 2 to the power of 4, so let's look at row 4. Row 4 will be the coefficients for our expanded binomial. We start with x, the first term of our original binomial. Each term is multiplied by x. The first x will be raised to 4, and for each term, the power of x will decrease from left to right by 1. Likewise, each term is multiplied by 2. But this time, the first 2 will start out with 0 power and increase from left to right to 4. Notice that x decreases in power while 2 increases in power. And each term has powers that add up to 4, our original power, so there's never any confusion. If we simplify our terms, we get, which is the same answer we would get by distributing. You can even imagine the triangle like this, since this would be the binomial expansion for each row with variables a and b. Thanks, Pascal. Wait! My homework had another problem! My triangle will be huge! Never fear, the binomial theorem is here. This was derived from the triangle we just used. Even though it looks like one scary, excited formula, you can use it to solve binomials with extremely large powers. While we're on the subject, imagine 7 friends show up to your party, but you only have 3 cupcakes. Oh no. If you wanted to randomly choose 3 friends to give the cupcakes to, how many groups of 3 could you choose from? By looking at the 7th row of the triangle, we say this is the 0th element first and so on to the 3rd, and there would be 35 different ways to choose a group of 3. In probability, this is a combination, and can also be written as 7 choose 3, which corresponds with the formula we found in the binomial theorem. Evaluating this expression also equals 35. If you take a closer look at Pascal's triangle, you'll also find cool patterns. Taking the sum of each row equals consecutive powers of 2. Let's evaluate 11 raised to the 6th without a calculator. Take a look at the 6th row and multiply each element by a power of 10, starting with 10 to the power of 6 and ending with 10 to the power of 0. Evaluate and add up each product. Indeed, this is 11 to the power of 6, and you can even check for yourself. So by taking the decimal expansion of each row, which is what we just did, we get the powers of 11. In the second diagonal row on each side, we notice the counting numbers, or natural numbers. If we shade in all of the even numbers that we see, this can go on for an infinite amount of time, and doing so creates Sierpinski's triangle. This is a fractal, which is basically just a repeating pattern, in this case never-ending triangles within triangles. Shading in the multiples of 3 produces a different fractal. Same with shading in multiples of 4, 5, 6, 7, and so on. And when we add up diagonal lines, we get Fibonacci's sequence, which is seen in real-world contexts like nature and astronomy. What will you find next within this mysterious triangle? Until next time.